Hello, everybody. My name is Maciej Hruszowski of Red Hat Research, and I would like to welcome you to another Research Days event. This is the last one of 2022. Today, it's my pleasure to introduce three gentlemen. First, as a speaker, let me welcome Georgios Kousioris of Harokopio University in Athens. Joining Georgios as our two conversation leads are Red Hat's principal software engineer, Luis Tomas Polivar, and Yanis Georgiou of Ryax Technologies. Gentlemen, with this, I leave the stage to you. Welcome.
Thank you all. We're very happy to be here. Let's proceed with no delay. Oops. Okay. So we'll be presenting. We'll be presenting a couple of aspects from the physics project. So we will start a bit with a small introduction to EU projects. Then we'll present the consortium and the general approach of our project. An initial view of the components, especially for the user layer, some research topics and results, and we'll follow up with the Red Hat role and presentation from Yanis for Kubernetes image layer scheduler. So in terms of the EU projects, of course, there are many different types. The ones that we are primarily involved are three main types: the research and innovation actions. So this is typically the, let's say, the most research-oriented category. This aims to deliver prototypes and integrate the environments with a TRL around 3, 4, and sometimes 5. Then there are also some extended innovation actions which they can start also from previous RIAs or from artifacts that come from previous RIAs. And the target is to increase the TRL in that case or start initial exploitation activities. And finally, the support actions that aim at having kind of orchestrating project that undertakes standardization or dissemination for a number of the projects of the previous categories. The budget sizes typically depend on the EC calls for proposals. Ideally, in RIAs can be 5, 6, 7, 8 million. In EAs a bit less, around half of that, and CSAs are around 1 million. In terms of EC calls, they are centered around 7-year framework programs like the FP7, the Horizon 2020 that ended a couple of years ago, and now the current program, which is called Horizon Europe. What typically the EC does is that it releases a work program of 1 or 2 years ahead. It has the calls and the dates of these calls. And I have put as an example the call from in which physics participate as a proposal. So the idea there is that partners organize in consortia and they target a specific call. Typically, the call has some high-level scope. In the case of physics, this was about cloud edge continuum, and in general, it requires a balance between academic and industrial partners. Industrial being both large players as well as SMEs, and the balance between the activities, research, piloting applications, innovation activities, and exploitation. Typically, work is split into work packages. A work package can have, for example, around 100 person months, and then tasks inside work package that can have around 20 to 25 person months. So in terms of the physics project, the main challenges that we targeted from the proposal time was to be able to enhance the abstracted usage of service offerings and clusters that are scattered across different providers across the continuum. Also, a major goal was we target specifically function as a service. So how can an application be ported in probably an easier manner to new paradigms like the serverless approach. Also, a lot of investigation is done on the space-time continuum. So the space being the location of the execution, time being the duration of that execution, and all the involved trade-offs that one can do in order to go to a more optimized resource selection from the global perspective. And then at the local perspective, how this operation can be optimized with better scheduling, for example, better co-allocation, etc. And in the end, to have multiple exploitation channels and be able to reuse artifacts coming from any part of the platform. So in terms of the specific project goals, initially we have the goal from the user layer to support visual programming environments so that one can create these serverless workflows, also taking into consideration and using reusable bits of code that we call patterns, and to have also a number of increased semantic annotations so that they can instruct the lower levels with relation to their preferences in terms of scheduling decisions, importance, optimization goals, and so on. In terms of platform and functionalities, the main operation here is to orchestrate and deploy the FaaS workflows and to optimize this cloud-edge interplay, and at the provider local layer to be able to optimize the execution of the containers inside its cluster. In terms of the project overview, as I mentioned, it is a specific call with a goal about having the cloud computing continuum. It's a RIA. It has a budget around 5 million. It runs from 3 years. We currently have almost 1 year and something left. We are 14 partners from large players like GFT, Atos, HPE, Red Hat, Fujitsu, and Byte, to SMEs like Rex, Incubate, etc. And then the academic partners like UPM, us, and DFKI. In terms of the project plan, we split the project in 5 phases. We are currently finishing phase 3, which is initially collecting feedback from the first round of the implementation. And we are about to enter the second phase of the second iteration of the implementation. So any feedback is more than welcome. You will hear more in the next slides. In terms of the technical architecture, as I mentioned, the 3 main technical layers are the user layer that includes the design environment and function DevOps process, the reusable patterns, and the increased semantics. You can see here, these are the task names inside the work packages. In terms of platform services, we have service for semantic management. So when you have semantics coming from the application and semantics coming from the resources, how you can match these two. We have placement optimization across the continuum. So at the global view, how we can have an application with different functions and whether these functions need all to be placed on the same cluster or in different clusters, how this is going to be separated. Performance analysis of the execution of these functions, data services that are for support in case someone wants functions that need to retrieve or store state, and deployment orchestration services to actually take the application workflow, the functions, and deploy them in the target clusters. And in the bottom, we have the infrastructure services in terms of the resource controllers, the semantics of the cluster to describe its capabilities, and 2 different layers of optimization regarding the scheduling based on the image layers. You will hear more from Yannis afterwards. And about another process about minimizing the co-allocation and interference. In terms of the project pilots, we have 3 large application areas. Initially, smart manufacturing. So the idea here is that we have a production line. The production line has an edge node. The edge node undertakes some role in terms of maintaining quality in the production line, and then checking different cases of failures and failovers to cloud-based versions in case the local execution is not as it is expected. E-health personalized monitoring and collective analysis regarding AI model inference for patient treatment and prognosis, and smart precision agriculture regarding digital twins, simulations, and resource management when it comes to smart farms. So how you can better optimize the use of water or fertilizers when you are growing the plants based on simulations that are run either at the edge or at the cloud. So in terms of the entry point, the physics design environment, the goals initially was to enhance, abstract, and enrich the FaaS application creation. So this includes primarily a customization step, so using, let's say, the repositories that we have in the project, how can a developer customize their own function environment, so in principle, how to start from their own base image, import the Docker file, things like that. Then specifically, we target how to simplify the creation of complex function workflows, which is a large challenge in FaaS today. Applications in FaaS have been measured to be around up to 5 functions in over 80% of the cases. And this, one of the reasons could be the fact that it's very difficult to write complex workflows. So you see on the left here, the way you would write a simple sequential, let's say, flow with 3 functions in the Google Cloud Functions service. You need to use YML type of files. So one can understand that if you want to design a workflow that has 10, 20 functions, it's practically impossible for a human to do that in a YML file. What happens if you want to have joins or other complex workflow primitives? It's very difficult to do it in, let's say, text-based manner. So one of the goals is, of course, to simplify that via a visual programming environment. Also, the idea is how to exploit reusable patterns, so pieces of code that can be dragged and dropped in the environment. We have some examples afterwards for that. How to increase the semantics, and how to abstract the overall packaging, testing, and the deployment process. Typically, our use case developers are, they're not hardcore cloud engineers or developers. They are primarily data scientists, scientific engineers that may be, well aware of Python or other technologies, but in the end, they would need a large learning curve in order to package things, test them, deploy them let's say, in a different paradigm like FaaS. So the baseline technology we are using for the design environment is Node-RED. Node-RED is a programming environment for event-driven applications. You can create workflows with functions, primarily in JavaScript. It has built-in nodes that come with the main version that have some typical operations. It has extension nodes from NPM, and one can also group functions and offer them as subflows, so abstract their usage. This is one of the features we use mostly. The main point here is that it has a combined workflow orchestration and function execution abilities, meaning that we use it as our main execution runtime, so one can create, let's say, a function based on a Node-RED flow, and then we package the whole Node-RED environment and send it for execution. But it also can be used as a choreographer or orchestrator functions. So you can have a flow that orchestrates the execution of other functions that are available on a FaaS platform. And that orchestrator can run either in a, let's say, a service mode or in a function node itself, And we have primarily OpenWhisk as the main execution layer for FaaS, and we exploit the ability to have custom container images for functions. In terms of the physics design environment lifecycle, so the design environment is split into 2 parts. Initially, you download the compose file. This compose file spins up 3 different containers in your local environment. These containers involve the Node-RED container that is the typical baseline version available from the Node-RED project, in which also we inject a number of patterns and annotator nodes, the extensions to the palette that we have created. So we don't break compatibility with the Node-RED container, but we add our additions as palette elements. The web interface in order for the user to do all the operations, and a component that does the main interaction with the backend. So the backend consists of a number of systems that have to do with code repositories, Jenkins pipelines, buckets for min.io, and Docker registries. So when the developer starts creating their flows inside the node container. Then they can go to the control UI and do a number of operations like build, for example, an image from that flow they have created, in which case the serverless, the SFG component undertakes the role of contacting the backend and pushing any differences in the code, uploading the flow to a bucket, and then triggering the Jenkins job. And the Jenkins job, on its behalf, it gets the dependencies and all the environment that is needed for this function to execute appropriately. It gets the flow that represents the function. It builds the image, and it pushes the image to the registry. I have also included a bit more information about the backend, but in favor of time, I will skip it. So in terms of the design environment, we have a full video available in this link. You can see the different phases of the function creation, build management, testing, logging. Just show a small, let's say, demo now, or at least go through the environment. This is the main, the admin panel, which has all my different flows. The flows are created inside the embedded node container. And inside in the palette, we have all the physics additions start from here. So it has, for example, some helper flows, how to get replies from asynchronous APIs. It has some skeleton interface nodes that are needed by OpenWhisk. It has annotation nodes. For example, if you want to define the size of the function in terms of memory, of timeout you want to apply. And here the main code of the function. Now, if I go to the, of course, you can have also much more complicated functions that you can use in your development. So if we go to the admin panel, you can see that now I have the history of all the builds that have been created, the different versions of this function, and I can rebuild it. And once I push build, I can go directly to, I will have a link to go to the Jenkins job in order to view the progress of that build. Okay. So it has a number of stages, and I can see this progress. Let's not wait for that to finish. Once it finishes, we'll just add a new line here with a new version. So then I can go and test it. So I can select one of the functions we have here, and I can just do the name and involve it. So this triggers the execution of the function directly on OpenWhisk. One of the things here is that we have two Jenkins pipelines. So the first one builds the image, and the second one is responsible for registering the image to OpenWhisk. We build in that way so that we can afterwards also change the baseline execution. So if one wants to use a different baseline, let's say, platform for execution, then they could have a different pipeline to a different registration process in different platform. And then probably we need a kind of adaptation to the interface that is needed by that platform. But in general, it's much easier to split it like that and, let's say, be able to support more baseline platforms. So you see here, I tested it, it worked, and I can also see the logs from all the available services, communications, and I can see also the logs from this one, from my container, okay, that executed for cases of, let's say, if I need some more information. Also, we can build applications. What we mean by applications is graphs with which we can create a graph, and from the build flows, we can select one or more and send them to the platform. What this does is that it basically makes the platform treat all these flows as one application. So if we do an optimization placement, it will take under consideration all the different functions in that application. So it's more of a logical management of all the flows together. Sorry. How about in the slides as everything. So in terms of patterns, what we meant by patterns is exactly these abstract subflows that you can drag and drop into your code and reuse them. So we have a number of different created patterns with relation to parallelization. I'll show you an example afterwards. To context management. So if you have warm containers, whether you want to reuse the context in that container for some reason. Data collection pipelines that offers a set of functionalities like retries of local storing, etc. Request management, if you want to somehow consolidate the requests. Workflow primitives in order to be able to join messages coming from different branches in a reliable manner. So what we do in general in the case of a pattern, we start from a concept. So in this case, the fork join parallelization primitive. We start thinking about how we can map that to an event-driven, function-oriented implementation. So in that case, we need an array input that has the different, let's say, rows that we want to execute. We have a split function that creates the different individual messages. The FaaS invoker that triggers, let's say, the execution based on each message, so it creates n different function containers. And in the end, a join function that joins all the results. So once we have the concept, we proceed with the implementation, and then the implementation is offered as a subflow here. So then you can drag and drop it, like here, in one of your functions without having to know how this works, but only having to parameterize it. For example, what kind of split size we want, what kind of execution we want. So you can have a FaaS-based execution, you can have a local multi-process execution, what is the inner function name to use, and so on. But just the parameterization information. In terms of available semantics, we have various flavors in terms of defining relative placement of different functions in one application. So affinity or anti-affinity. Locality, if you have different available clusters, if you want to specify concretely that this function needs to go to the edge, the other function needs to go to the cloud. Importance in terms of scheduling, optimization, goal for the performance energy trade-offs, sizing of the function, other architectural requirements, monitoring, and so on. And interface to any data services in order to take under consideration data locality, for example, when we are doing the placement. And one of the features of physics is also the RAMP, the Reusable Artifacts Marketplace platform. So this is a catalog in which we upload any relevant physics artifact, and by any, we mean any. So it can be an operator, it can be an ordered flow, it can be a data set that we acquired, the service, semantic model, etc. So inside this catalog, you can actually go and see the artifact itself. It has links to repositories on GitHub or usage guides, and you are able to directly download and use it. So if you are interested in using some of the artifacts that interest you more, we are looking for feedback, as I mentioned, in this period of time in the project. So if you want to mention some bug or some fix or some specific extension, we also have that capability through the RAMP to request a specific asset or to request an extension to an available asset. This is doable through the RAMP. I have time. So in terms of the performance aspects, the space-time continuum we mentioned, I present here a kind of a summary of things that we did during the first 2 years. So an initial experiment we did was to try to measure different function orchestration or choreography overheads in the different modes that were available to us. So one mode was to use the OpenWhisk sequence operator. In OpenWhisk, you can define sequences of functions. This means that OpenWhisk undertakes the role of invoking the functions and then passing the output to the new function in the sequence, etc. Now, obviously, this is a bit limiting because it can only support sequences. The second mode refers to our usage of the Node-RED runtime, both as a orchestrating, let's say, function, but also as an execution environment. So in this case, you have functions running inside the Node-RED runtime only. So this gives you the benefit of being able, through a suitable, let's say, flow creation, to support all different workflow primitives like joins or branches and things like that. But of course, you have the, let's say, the drawback that you can only have parallelization inside the scope of the same container. And the third mode was to use, let's say, an orchestrating flow inside Node-RED that invokes functions that are external to Node-RED. So any function that is deployed on OpenWhisk. So in this case, you get both benefits of having full primitives and the ability to have full parallelization, meaning that you can spawn, many different containers, and you can have, let's say, trade-offs between executing a function here or spawning different instances of that function, like in the fork join case. But of course, it comes with a trade-off here that if it's, for example, the outputs that we had, you typically need, in this case, at least in our experiment, around 100 milliseconds in order to provision that container. So this is useful information for someone in order to do the trade-off around how they want to implement their workflow. So if they have something that is relatively small in computation, they would probably go for that mode. If at some point it gets bloated up to large computation, only in that case to use the parallel mode. Also, we create a specific load generator for OpenWhisk. We implement it as a Node-RED flow, but it can also be run as a function if run on top of, let's say, the OpenWhisk interface. One of the main features is that it supports function chaining. So if I remember correctly, for people that are in the call and are involved in Knative doesn't have a function timeout, if I'm not mistaken. OpenWhisk does. So if you want to do a load generator that starts an experiment and you need to bypass that timeout, you need to implement it using the function chain pattern. So to have, when you reach the timeout, to have successor functions that undertake the remaining part of the execution. The useful thing here is that we extract around 15 different metrics from that. So we get metrics that are directly given by OpenWhisk when we get back the activation. So like the wait time in the system, initialization time for the container, duration of the function itself. We get a number of other different timestamps across the process so that we can extract and calculate other valuable metrics. So if we set a specific rate, did we actually achieve that rate? This is primarily to see if there's no bottleneck at the generator side. We get information about the total, let's say, user side delay. And from that, we can estimate the network latency. And we get a number of other validation, let's say, scenarios. So if we want to, if we have a limit per load generator that can reach, for example, 100 messages per second, and we need 500 messages per second, we should launch 5 different load generator functions. But in that case, we need to ensure also that these functions get activated around the same time. So if you're not able to launch the 5th function because there's no room, for example, in the container cluster, then you should take that into account in the results. So we have also the actual start time of the load generators in order to validate the actual client concurrency. And we also did an experiment based on one of our use cases. So we had an AI inference function that was deployed in 3 different locations. So one internal edge type cluster with a very small amount of resources, and 2 available clusters on Amazon and Azure that had different characteristics. So by triggering the load generation towards these target endpoints, we were able to identify sizing considerations. So, for example, that specific function needed over 256 megabytes of memory. If it didn't, it failed, especially in Kubernetes clusters. We were able to, without knowing the internals of the cluster, to not actually estimate, but detect what are the main cluster characteristics. So which cluster has the best performing instances, which cluster has larger, let's say, more container slots from the wait time, which cluster is further or away in terms of the estimated latency. We're also able to see misconfigurations. So in the case, for example, of the Azure cluster, even though we had more nodes compared to the Amazon one, you can see that we had more wait time in the system for the same amount of traffic. So this means that for some reason we had less container slots available for the FaaS platform. And it turned out that we had forgotten one of the configurations to be the default one. So even though the node had 32 gigabytes of RAM, we were actually only using 2 gigabytes of them for the OpenWhisk platform. And also other cases like the concurrent containers effect. So these 2 columns here indicate different numbers of containers. So in this case, we had about 20-25 concurrent containers running on the node. And in this case, we had around 5 or 6. So you get, basically, due to the concurrency effect, you get around 7 times worse performance, which is something to consider also when deploying different containers. And other interesting things was about how the increased memory can affect or not the performance, the execution of the function, and many other things around latency and so on. So I think this concludes my part.
So I take it from here. Now that George has explained like the higher level overview, I'm going to talk a little bit more about the Red Hat role and the main technologies. Red Hat usually in this kind of project gets involved in kind of 2 different, it's in more, but usually we target the infrastructure layers as well as the integration. So in this project, we have also taken kind of this approach, and we have worked with the lower layers of the stacks, meaning like the Kubernetes cluster, the multi-cluster orchestration, networking, etc., and also to enhance the infrastructure APIs with the needed extensions by the other partners and the other components in the physics architecture. And that means that we have work also on the integration, like for instance, we have worked on some custom resource definition and operators to have some new APIs that can be used between components, as well as some Kubernetes webhooks that we use, for instance, to change the scheduler that we use for some pods, as Janis is going to explain later the benefits of that scheduler. Regarding the technologies that we have been working on, it's Kubernetes as the core, of course. We have a couple of clusters running on different locations. One actually is in Amazon, the other one is in Azure, and we have different Kubernetes versions in there. We have OKD, and we have also a vanilla Kubernetes in them. And we have used both OCM and Submariner for the multi-cluster setup, for the orchestration and for the networking. We have also investigated things like Microsoft for low footprint Kubernetes devices for some of the use cases that we have. and of course using like Prometheus for the data monitoring and getting some information from the infrastructure and the applications that need to be used for later optimizations. As shown before, we also have OpenWiz at the function as a service, and we have worked on Kubernetes operators and webhooks as a way to manage our application and components that run on top of Kubernetes and to provide these extra APIs to the other components. If we get a little bit more on the components here, we have a figure where we see like a couple of well, actually the hub cluster and a couple of managed cluster in there, and some components here and there. The green ones represent what is already there, like using OCM, Submariner, Kubernetes to do the multi-cluster setup. And then we have some red component in there that is related to OpenWiz or some proxies that we have built in other work packages where actually Red Hat was a little bit less involved. And then the green one was actually the work package that the components related to the work package that Red Hat is more involved in. We have one related to the semantics, which basically gathers some information about the cluster itself, the different nodes, and pass that information to the central hub cluster so that it can take better decisions about what is the best location for a different set of functions. We have the webhook that we use to be able to enforce the schedule that we want to use, as well as to do some co-location optimizations that will provide some hints for how the pods or the functions need to be either co-located with affinities or anti-affinities, and the workforce CRD operator that is in charge of providing this API and do the needed actions to actually register the functions in each cluster. So what happened, just to try to show a little bit more the registration flow, is like in the hub cluster, there is a manifest word using the LCM functionality to perform like the actual function creation, and by using the semantics information, we choose one of the clusters and we inject in this manifest word our workforce CRD is our YAML with the API that we agree on. Then the selected cluster will realize that this has some work to do and go to apply this workforce CRD object in the manifest word. And once that happens, what happens is that it triggers the reconciliation loop of our operator, which in turn process this object and calls the OpenWiz API proxy that we generated to actually register the function. And once that is done, it actually gets some information into the status section of this CR object, so that it can be passed back to it. It's stored in the local HCD class database, of course, and it can be passed back to the hub cluster for tracking it down. And for the function registration, what we have is that we have something called in OpenWiz to execute a specific function, and the way it usually works is that either there is already a warm or a hot container that can be used to execute that function. In that case, nothing needs to happen. But if this is not the case, it will call the Kubernetes API to generate a new pod where this function needs to be created. And when that happens is when our webhook actually kicks in and do some extra actions in there. First one is based on the annotations that we pass from the upper levels of these components. It will choose the preferred scheduler, Kubernetes scheduler to be used for this pod. In this case, using the layer-aware scheduling algorithm that Janis is going to present after. And also to execute the co-location engine that it will pretty much decide on some co-location strategy for it, meaning that it will set some affinities and anti-affinities hints on this pod spec. And with that, the webhook finish, the pod spec is stored, and then the normal Kubernetes process happens. It will realize that it needs to use this scheduler, and this scheduler will select the proper node, which actually has more layers of the container in it, so that the pod can be created fast enough, and the function gets executed on top of it. And this is more or less the main area for Red Hat. Now I pass the floor to Janis to deep dive a little bit more on their work on their side.
Thank you, Luis. Okay, so let me go a little bit deeper into the way the scheduling takes place within physics. So you may have a broad idea from what Luis and George just presented, but in general, what we propose here is a two-level scheduling procedure where the placement of the application components can be performed. The first level of scheduling is going to be on the global level, where we are going to decide which of the, let's say, individual clusters are more adapted to execute our functions. And then the second scheduling level is going to be on the local level. There we have the actual Kubernetes scheduler that is going to be interfered, and where we enable the selection of the most adapted node in this particular case, considering different, let's say, optimization techniques. Okay, and here in the example in the right, you can see that, for example, the graph that we have initially, it is deployed upon the nodes, firstly selecting which of the clusters we want to use. For example, there we can have resource constraints, such as, okay, we really want that task one needs to go to edge resources. This passes as constrained, and we have the selection afterwards. And then once we are within the local scheduler, then the local adaptive scheduler that you can see on the lower level selects which of the nodes are more adapted based on the annotations or the different characteristics that we may have. We can move on, Luis. Okay, so let me give you some brief details about the global continuum placement, and we're going to dig a little bit deeper into the second level of schedulers afterwards. So initially, we have implemented the first version based on a multi-objective scheduler, allowing different objectives such as performance, energy to be taken into account. This allows us also the expression not only of constraints, but also resources needs coming from the applications. The code is currently published as open source. The link is there. And we are currently working on optimizations based on linear programming. Initially, we consider this as an offline approach, but we're going to improve it further as we go, as we make progress here. So you can see an example on the right with a Pareto curve where we try to minimize make span and the amount of the downloaded data. These were some initial objectives that we have set, but our policies are adaptable to different objectives. And currently, we have an article being prepared to be submitted for CC Grid next year, CC Grid. So in the example that you can see on the right, you can see that with linear programming, we can have multiple iterations, and you can see that with the third iteration, we reach our optimum, which is the cross from what you can see, which is the lower that we can go in the make span, and the lower we can go with the amount of the downloaded data. Okay, whereas if we go larger, then this we go beyond the optimum, which is not what we want. Okay, we can go on the next slide. Okay, now on the second level, on the local adaptive scheduling, what we focus here is, let's say, intelligent algorithms that will enable us to bring forward the FaaS characteristics and particularities about FaaS executions. Okay, so things such as, we are interested about things such as cold starts and co-allocations and stuff like that. So based on our initial results, based on our studies that we have done, using simulations and observations, you can see some examples using function benchmarks on the right here. And so we have observed that a lot of times with with fast executions, at least with the function benchmarks, the download may take much more. The download of the image may take even more time than the actual execution of the function. Okay, so this is something that we wanted to address, and so our first algorithm within, let's say, the local optimizations was to minimize the delays due to image downloading for this function execution. Okay, so minimize cold starts. Now, Kubernetes already provides an image locality plugin, and what we have done is we have implemented a variation of image locality plugin, taking into account on the one side the existence of containers layers, and trying to favor the execution of the functions on nodes where layers of the containers that we want to deploy exist already. Okay, and this new scheduler is named layers locality. Luis, can we go to the next one, please? Thank you. So if we go a little bit into the implementation, into how we did that, so we actually need two things. The first one is to get the available layers on each node, the name and the size, okay? And then for each new pod, we need to compute a score per node, considering the cumulative size of already available layers, okay? So for this, we had to make changes on different areas of the involved software. First of all, Kubernetes internal interfaces to add the layers. So we currently have optional layers filled within the particular core node status API, and this is what we used. And then the second thing was, of course, we had to select a particular container runtime interface. In our case, we went with Cryo, and within this one, we adapted to get the available layers name and size on the node and send it through annotations. Okay, so we did not make any particular API change. But of course, this is something that we can think it over how the, let's say, the ideal implementation would be. We can move on, Luis. Now the code is open source. You can find it in the links here. We have a documentation to deploy it on vanilla Kubernetes, and we also have all the changes done on particular forks of Kubernetes and Cryo. Now, what is interesting here is that we think that there is a lot of value in this new layers locality plugin, and we have started discussions with the SIG scheduling Kubernetes group to push this scheduler to the upstream Kubernetes. We have already had some exchanges, and based on their inputs, we are going to adapt our implementation and try to have it within Kubernetes before the end of the project. Okay. So currently, we are working on experiments to compare the new scheduler with a typical Kubernetes scheduler, and show how the performance improvements for specific, FaaS applications, and also continuum of edge cluster, edge and cloud resources. So that's more or less what I had on my side as well. Thank you very much for your attention.
Good. I see there is also a question on the Q&A that I didn't find the button to reply in there. It's from Ahmed, and it's about just highlighting the fact that now Knative has it's more mature and has more functionality like Kubernetes, Knative functions and these kind of things, and related to if we have evaluated this more recently. Just to mention here that when we started the project, we did some evaluation to compare like Knative, OpenFaaS, OpenWhiz, and actually one of the main reasons to go for OpenWhiz at that time was that the functions were not supported at Knative at that time, because the project, as George has presented, was based on function as a service, not on serverless, and that was kind of the different, maybe if the project started today, that could have been different, I don't know. But yeah, and we keep taking a look to this, and we have some plans to try to also support it. We have kind of abstracted away a little bit by using this workflow CRD operator, and maybe just a matter of adding a proxy to it, and then call knative for creating the functions when we register them. So we definitely want to take a look at that and see if we can also leverage like the new fancy features that you pasted there. Like it seems that they also have something for reducing the call star times. And I think it was also you mentioned something about the timeouts.
Yeah.
So, do you want to add something?
Is there a question?
No, I'm not sure if I missed any other question. There was another one about the load generator, that it looks like you could program different load patterns and perhaps the different type of loads like TCP, UDP. Is that correct?
The moment the load generator basically tries to, the main element is doing HTTP requests. So potential, but if one changes a bit the inner action that is done by the load generator, then it could probably be extended to support different kinds of operations that we want to do. So the main benefit of the load generator is that it is packaged as a function, and this gave us a lot of flexibility and ease of deployment, because we deploy it as any other function. So we had from previous projects work going to load generation with let's say more traditional tools like JMeter, and it always needed to have your own separate load generation cluster to handle all the aspects of the containers. It needed a lot of administration, let's say, and a lot of installation, configuration, etc. Now with the function packaging of the load generator, it's much easier for us to port it and install it and scale its use also. So these were the benefits. So in terms of the internal operations, we mainly do HTTP calls, because that's also we target at analyzing the functions. But probably if someone just changes inside the operation that it's done, it can also be extended to have different triggers.
Also, thank you. If there is any other question, or if you just want to jump in and with your question live in the platform, let's go for it, or write on the chat, whatever you prefer.
Hi.
Hello.
So this is really interesting. Thank you for going over such a huge project in such a short amount of time. Appreciate sharing the information. I was wondering how you handle the issue of reproducibility, since you have multiple clusters and the software and hardware is obviously changing out from under you while you're doing this. Do you handle it by ignoring it and doing statistically large numbers of tests, or do you log all the versions and everything of what you're running on in a particular run? What's your approach for that?
For which part?
To make the experiments reproducible by somebody else.
Yeah, I think the problem in that case is that we are running it also on top of Amazon and Azure, so we are not really aware what else is executing.
Right.
That's a problem. Our main concern at this point was not so much to get the actual estimation as to whether it's and used in the future, was mainly to understand a bit the different metrics that were involved in FaaS, and also to be able to see what. So, for example, we were looking at metrics for using in auto-scaling decisions. So through this series of experiments, it was much easier afterwards to understand the whole operation of the system and conclude to more concrete metrics that we can use. The issue of reproducibility is very difficult when you go to something that you do not control. I think the major, let's say, point that we tried to do also in the load generator was to take every possible measurement step in the process, so that we can have all these validation steps. So in terms of the set rate, okay, the set rate is set, but is it achieved? It's based on timers in JavaScript. Timers are not accurate; they are the minimum amount of the delay, not the maximum. So, do you actually do the rate that you set? That was one issue of reproducibility we decided. And also the other issue about if we scale the use of multiple load generators that would be supposed to be running at the same time, so generating 5 times the set rate of each load generator, if they indeed start at the same time, because if one of them hits the container limit, for example, and needs to wait in the queue, then obviously you don't have 500 operations per second, you have 400. So that's what we try to do, to be able to get as many logging points as possible, so that someone can review the results afterwards and see. Sorry, we have so to give detailed logs, so that someone can validate better the results in the end.
Did you consider having a bare metal cluster where you, as one of the choices of where you could run the function as a service?
So concerning, perhaps I could chime in here, concerning the scheduling related aspects. We actually use bare metal clusters, and to be more precise, we use Grid 5000. I don't know how.
Okay.
Grid 5000 experimental testbed. So where you have the ability to actually be certain that you are using these particular machines in a particular way. So and this will allow you to reproduce experiments exactly as you have done them initially, and so for scheduling, it's important to be to have reproducibility by default. And that's why for the, let's say, real scale experimentation that we do, we use Grid 5000. Now we combine this with a simulation environment, and for that we use particular software such as SimGrid, if you have heard of it, and BatSim, which is another one that goes upon SimGrid for scheduling. And so we first do our simulations using the simulation software, and then we pass on the experiments, on the real scale experiments upon Grid 5000.
Okay, I see. So there is an option if someone is concerned about reproducibility to go in a more controlled environment.
Right.
Cool. Thank you. Right. I hope George and Luis are okay.
Yeah,
this has never happened before.
We had our general assembly today for physics project, and they are in a particular area, all of them. So yeah. I suppose that they will be able to join in a while.
Yeah, there was another comment from Ahmed. I don't know if he wants to join or if he's in that same building. But Ahmed, if you're here, maybe you could join and talk about your Knative comment.
So I'm reading this right now.
Yeah. Okay. Yeah. I see. Actually, initially we were wondering. We did some studies, and we were wondering if we should go with OpenWhisk or Knative. And the reason we went for OpenWhisk was perhaps there are multiple reasons, but one of the most important was the fact that we had the ability to use workflows with OpenWhisk, whereas with Knative we did not have this option. I don't know if now we do. I must admit that I'm not following very closely Knative. Perhaps Ahmed could comment on that. But yeah, of course, on the other side, the fact that Knative is a native Kubernetes FaaS, that would facilitate us a lot, and we would directly use all this optimization that you mentioned, Ahmed. But again, it was important for us to have the workflow related features that OpenWhisk gave us, so
Right.
we selected that.
And Stavros says there is Cogito integration and serverless logic as a workflow option. So it sounds like
Okay, what is Cogito? I have no idea. I do not know this. Is it a software?
Stavros, do you want to join and talk about that?
Cogito integration.
I haven't used it myself, so I can't say anything.
Is it a Red Hat? Is it a Red Hat product?
It's an open source, but I'm sure there are Red Hat people working on it.
Okay.
He provides the link to it.
Okay, yeah. Yeah, right. Okay, I was not aware of that. That's interesting, very interesting. I'll check it out.
Yeah. And this is the challenge when you have a project that's a several-year project with a really large infrastructure, and things change while you're in the progress.
Exactly. So initially, we, as George explained, we usually do a state-of-the-art in the beginning of the project, and then we try to adapt it or to update it as we go further. But a lot of things might appear during the first year. So if you have made some choices, then it's difficult to go back and turn around.
Yeah. So if people want to get in touch with you and update you on things that they think would be interesting, do they just drop you an email, or is there a chat room, or what's the way for people who aren't already in physics to interact with you?
So in general, there are some channels. We have LinkedIn, Twitter with physics, where you can find us, and then email directly on a contact within physics, or directly to us, Luis, George, and myself. We can. It will be very interesting to have your feedback.
Okay, good. Yeah, and I think your links will be posted on the Research Red Hat site that goes with this event too. So
exactly. So I suppose, I'm not sure if this has already been done, but I suppose the slides will be online somewhere within the Red Hat Research Days, and there you will have all our contact points.
Yeah. The slides and a link to the recording will show up later.
Yeah.
Super. Okay, well, this is an interesting ending.
Yeah, sorry about that. Really sorry about that.
Sorry. There is another question from Helio or Elio. Yes. Sorry, I'm not sure.
Is that something related with the rules decision maker?
He's just speculating, or she's, I think it's a he, speculating about the Cogito. Thank you, Helio.
Yeah.
Okay, cool.
Okay.
Well, thank you very much for
Thank you very much, and really
Is-
sorry for the
Matej,
ending.
are
I
you
don't know
are you
if
still
you
here?
want to. Yeah, if you want to wait a little bit longer, I suppose they will try to join again. I mean, yeah.
I'm going to leave. I don't know. It's up to Matej.
Okay.
So, Yanis, what do you think? You wait.
I can take any questions if there are. We can wait a little bit. It's up to you. I see that we can wait 2 more minutes, let's say, and if they don't join.
I don't see any other questions at the moment, and Luis is not replying. So I'm thinking maybe they had to leave the building and they don't have a connection.
Perhaps, yeah. But I mean, I would suppose that they could also connect with their smartphones or something, no?
It might be hard with the smartphone. We haven't tested that.
Yeah. Okay, since the slides are going to be online, you can always ask questions afterwards. You can contact us offline. And it would be interesting to have more feedback about what we have presented.
All right, so let's close this out. If there are any further questions, there will be contacts for our speakers.
Perfect.
You can reach out to them. You can find the recording and
Actually,
the slides.
There was one more from Helio.
All right, let's do that one.
Helio asked whether you're using JavaScript or TypeScript in your functions.
Yeah, currently, you know, the fact that we're using Docker to build our functions makes us polyglot. So you can actually use JavaScript or TypeScript for your functions. Now, I don't know if the current examples are done with those languages. I think that we mainly use Python. But you know, architectural wise, since we go through Docker, you know, we are completely polyglot, and so you may have one function in let's say JavaScript, another in Python, another in Go, and they can all be part of the same workflow. Thank you very much. Okay.
All right, so many thanks, Yanis, for finding your time today to present. Yeah. I'll extend my thanks to Georgios and Luis offline.
Yeah.
And as always, you can find the contacts online on our pages. The presentation slides and recording will show up there once it's processed. And reach out. And thank you for coming today.
Thank you all. Goodbye. Have a nice day.